Okay, so this lecture will cover materials. This follows on from the rendering lecture series, and materials and lighting are kind of go hand in hand to some degree. We will talk about lighting in more depth in a different lecture, but materials is primarily the response of the surface to the light, and so that's kind of where we'll keep our focus. This will also be a little bit different than, say, the rendering lecture, where now we will look at both the theory behind it and actually what we do in Unreal to modify the materials. Okay, so kicking off from kind of where we finished with rendering, we start with a texture mapped triangle where we know the color. And so color is kind of the most basic form of the material, but there's quite a bit more that goes into determining actually what a material is and what it returns, right? So the difference between, say, cloth and metal or plastic or soft or hard surfaces and all these things, they all matter to the way the material actually looks and the way that you perceive the material, and really the way the light bounces off the material and the way you perceive that. So what happens is we encode this as what's known as the bidirectional reflectance distribution function, or the BRDF. And this function captures everything that happens, or almost everything that happens, when light is projected onto a surface and then bounces on that surface, and maybe some of it is scattered, some of it is absorbed, and some of it might be purely reflected. So scattering is a little bit different. It's like it's partially absorbed and then bounces back out in a slightly different way, right? Okay, so at each point, when we are properly computing, or at least computing a better model of our light material interaction, then at every point, every one of these pixels for the surface where we're trying to figure out what color it's going to represent, rather than simply saying, I'm going to pick a color and send that back to the viewer, I'm going to go through this whole function, this BRDF, which takes into account both the light which is incident on that point, so that you've got WI, and then the light that gets reflected away from that point, the WR. And we'll see the various kinds of complexity that we can add, the simplifications and complexity, that represent different models of light and different levels of complexity, different models of material in some sense as well, depending on how the material responds to the light and how it reflects it back. At every single pixel, we're doing this entire function calculation for each point of light. And yet, because of that, we can get some pretty incredible details. So if we consider the texture map, in a way, that is the easiest version, right? So we actually don't care about WR. We don't care about WI. All we're doing is saying that for when we're texture mapping a solid color without any reference to light at all, we're in a sense ignoring all of the light and all of the visibility and simply giving a color back. And that's reasonable. It's a first pass and we get the color back. And really, we're going to do the same thing, but now the color is going to be different depending on that. And because of this, because of the way we handle this, we're able to model things like plastics, or a cloth in some sense can be modeled this way, and some aspects of hair. So a lot of properties can be modeled simply by how we decide the light is reflected away from the material, or how it might be scattered, which means it's partially absorbed and then re-reflected out from a different location, or simply purely reflected at the point with a high intensity, and so on. So let's take a look at how this starts to look. So the first new piece of data we'll need is what's known as the normal, or the surface normal. And you can see the surface normals here represented as the blue or purple lines projecting away from the surface. These are always facing sort of directly perpendicular to the surface. If we look here, we see one that is pointing at this direction from it. The normals would kind of follow almost like a porcupine kind of look off of this surface. And the reason for that is that helps us to understand exactly at that point in space where its sort of flatness is. Okay, so if we look at a pattern like this, we've got large triangles, right? And really in the sort of early days of graphics, that's all we had. We had large triangles, and we would render uniformly across that triangle a normal for that surface. So you get this whole surface, this whole patch right here, would have a normal. We would render pretty much every color as though we had that normal, right? Again, sort of treating that, passing it into a function like this, and just coloring that entire triangle, and you'd hope for the best. But nowadays, we actually have a normal per texel in the space. Okay, so as we're trying to render down here, as we break up this triangle into texels, into really into the pixels, into the texels over here. As we start to rasterize that triangle, then on each point we can compute the normal. And so, so for each individual small piece, we sort of assume that it's for a very small localized region, essentially across the pixel. We assume it's flat there, and that's actually the tiny patch that we now use to represent it. So it's down to the single pixel level in some sense. So what we do is, at each vertex, we interpolate the normal itself, and so we figure out what that, given that the normal is like this tiny little purple here, this tiny little purple here, and we move across the triangle and interpolate the motion of that normal as we move through and as we rasterize that triangle and determine how that surface shifts, right? And so that helps us capture the curvature along the triangle. Now there's additional information that we can pass in, and we'll talk about that in a minute. If you've heard of bump mapping, you're probably already thinking about that. Bump mapping and normal mapping. But for now, this is a way that we could take this per vertex normal and start to map it across and get a better answer. So one of the simplest versions of lighting that we can use then is what's known as Lambertian diffuse. And this, in some sense, some respect, kind of models a very rough surface. So when you are thinking about lights, when you're thinking about the way that light interacts with the surface, you're thinking about probabilities, but you're thinking at such a large scale that you kind of go automatically to the scale of large numbers. In probability theory, the law of large numbers is that if you flip a coin long enough, you sort of get the correct answer back, right? So if we flip a coin 10 times, we might actually get 6 or 7 heads and 4 or 3 tails, right? So we're not really getting a proper model of the coin. But if we flip it 100 times, now we're getting something like 55 heads and 45 tails. And if we flipped it 1,000 times, we're starting to get much, much closer to 50-50, right? And actually heads and tails with US quarter are not exactly 50-50, it's like 51-49. And so if you did a large enough, you'd find out very close to the exact answer for a particular coin, which is roughly 50-50. So when we're dealing with light, each individual photon has some probability of being absorbed by the material, depending on which atom it hits within the material. It has some probability of being reflected, and then some chance of being scattered as well, which is that it actually goes in a little bit, bounces around, and then bounces back out. Right? So those are kind of the 3 different ways that a piece of light, a little particle of light, will interact with the surface. But we don't really care about individual particles of light, we care about the entire sum of light. And so what we do then is we calculate sort of the probability. Let's say it's a 50-50 of absorbing a light and scattering a light. And so what that means is that because what we're really dealing with are billions of photons in a beam of light coming from the sun, or even coming from your lamp on your desk or something, there are billions of photons coming out of that light source hitting the surface. And so of those billions of samples of this little probability distribution function, if we have a 50-50, we're just going to simply say that exactly half of those light photons do one thing and the other half do the other. So if we say that exactly half are absorbed and half are sent out, then that's what we do. And so what happens is then that given the initial intensity, which is really the number of photons, like the intensity is sort of correlated to the number of photons that are being sent per second, we would essentially have that. So you would get half the intensity. So based on that then, we can say that if there's a probability that you're going to absorb half the light given a certain wavelength, or color in this case, which is the wavelength, then what we see when billions of particles are being reflected at us is half of those. And so we see a half intensity. That's sort of the human level experience of this kind of effect. And so then what's happening with the Lambertian model is it says, well, we have a very rough surface. So you're not going to get any kind of spiking effect, as we'll see with some other effects, where you actually get a shininess out of it, where it's actually, you see a reflected light. Instead, the surface feels like it's uniformly lit depending on, or regardless of which direction you look at it. So the light's sort of just scattering away from the surface in all the various directions, because there's tiny little bumps on the surface, and so the light will scatter some of its amount to the left and some of it to the right and some of it forward and some of it backward and so on. And the only thing that we care about with Lambertian is what the direction of the light source is and how those rays, the beam of light, is being shot down towards us. Because if it's shot down directly onto the surface, then we get all of the surface reflected. So all of that power gets reflected directly out in all of the directions, right? So if we're coming straight down, then 100% of the light gets reflected all the way back in all the directions. Okay, so we don't have any absorption whatsoever. We assume perfect absorption along the colors that we care about, and recall that, you know, a purple shirt is not, in some sense, purple. It is a shirt which absorbs every color that isn't purple, or every part of the light that isn't purple. So if a beam of light which is coming in at the frequency that encodes red, and another particle comes in encoding green, then the green one is going to be absorbed, and the red one will be reflected. And so when we say 100% of the light is reflected, it means that 100% of the light is hitting the surface perfectly, and then either being absorbed, depending on the material of the surface, or being reflected. Now, if we come at it from an angle, it means that a lot more of the light is bouncing off the surface sort of uniformly and disappearing, right? So we kind of lose track of that light, or it gets absorbed in a weird way. So it's kind of a model for, you know, that once we start coming at it from an angle, either we're just completely missing the surface, and so there's no reflection, or we're coming at it from an angle, and because of the roughness of the surface, some of that light actually gets just trapped in the surface, so it's easier to grab. We'll just go with that for the sake of this class. I certainly encourage you, if you find this topic interesting, to investigate a physics course on light and the properties of light. And so what happens is then that we can use the angle of the incident light to determine all of what's happening. Okay. So if the light's coming straight down, if the angle to the normal is perfect, they're perfectly aligned, essentially the angle is 0, then we know it's 100%. And if the angle starts to fall off and we get down to 90 degrees, so if the angle of the light is 90 degrees to the surface, we assume that none of that light is now hitting the surface. It's now just simply sliding past the surface without ever coming, hitting the small bumps, and we're seeing it. So with that assumption, then it turns out that there is a function which kind of maps that perfectly, where we start at 1 when our angle is 0, and it falls off perfectly towards 0 as our angle reaches 90 degrees, and that's the cosine. So we take the cosine of that angle, and by taking the cosine, that tells us how much intensity we're going to use, right? So that's our sort of probability of the total intensity, and then we take the color of the light times the color of the material. And so this then is, in probabilities, you can think of when you multiply two things together, it's kind of taking the and, right? And if you add two things together, you're getting the or property of, if this or that, then I'm going to add the probability of this and the probability of that together. But if it's the probability of this and this, then I have to multiply them together to get the full probability. So this is saying the probability that I absorb purple, that I absorb green because I'm a purple surface, the color of the surface, or the reflected color of the surface, we're going to multiply that times the probability that a given particle has a certain wavelength of red or green or whatever. We multiply those together and we get exactly that amount of intensity of purple back. Okay? And then we multiply that by the actual intensity. So again, if we only are going to do about 50% of the light, then that's going to be captured by, say, this cosine property here. Okay, so we take the cosine of the angle of the light, and then we multiply the two colors together, and we get our resulting color at the correct intensity, and that's the result. Okay, so this is also known as the cosine law of light, which is that it falls off as the cosine of the angle with the light to the normal. Now, it turns out that if both n and l are unit length and only represent a direction, which is all we care about, because we only care about the direction of the light and the direction of the surface. We don't really care about any other sort of distance involved here. So we remove all distance and we just say the normal direction, which is a unit length vector, and a unit length light. When we dot them, we get the projection. The dot product is a projection. It is also essentially the angle between them. It's actually the cosine of the angle between them. So you can see that if I had a vector, if this vector was lying flat, and I wanted to do the projection with this vector, then I would see that my angle lying flat would just take up 0 length along this vector. Whereas if I had this vector pointing straight up, and both of them again are unit length vectors, and I do the projection, then I get exactly 1 back, right? So they're both length 1, so I get 1 back because this vector is now pointing up. If it's pointing halfway, then what we get is a cosine of essentially 45 degrees, right? The cosine of 45 degrees, I don't know off the top of my head. It's actually I think 0.7. Okay, so essentially we sort of get to cheat, and rather than having to compute the cosine, which it turns out is fairly expensive even for graphics cards to do, we can cheat and just use the dot product as long as we know that the normal and the light vector, the direction vector, are both unit length, or then we can use the dot product to get the same result as though we had taken figured out what the angle between them was and then taken the cosine of that angle. So this is pretty cool because we're going to see this a lot. This dot product is a powerful thing to use because of the fact that the cosine is used commonly in graphics, and then the dot product is very easy to calculate on a graphics card. Okay, so here it is again, just to make sure that you can understand it, that we do have the dot product projection, and it calculates really the cosine of the angle for us. And then in this case, because we know that we're using unit length vectors, normally the dot product is actually encodes not just the cosine of the angle, but also the length of the two vectors multiplied together. So let's take a look at that in Unreal and see how that looks. Okay, so from the Unreal side here, we're not necessarily going to write in a Lambert model. We're just going to see how we get something that is fairly close to the Lambert model as we were talking about from Unreal. So in order to do that, and we've kind of seen some of this already, we've sort of played around with these parameters, but to get a close approximation of a raw Lambert, and actually it's because there's quite a bit more going on with Unreal in terms of reflection and so on that add a lot of extra quality to the lighting. Well, let's just look at a simple scenario here. Let's set the light to about 50%, and then we'll bring that in as the color here. And we see something pretty close to what we're expecting, but let's go ahead and set our metallic values to create a 0 parameter here. We'll set both metallic and specular to 0, and then I'm going to create a blend parameter and set our roughness to 1. Okay. So given this, what we're seeing is essentially a Lambertian diffuse property, and we see the kinds of things that we'd expect from that, where here's the direction of light going this way, and we see a fall off as the cosine, and what we would see without anything else happening is that it would slowly degrade toward black, and then we would have no other color back here. Now what we're really seeing is a properly shaded sphere due to some other qualities here. So some of that quality is some ambient occlusion that's happening as it's capturing dark down here, and some of this light is actually being reflected off of the surface here, right? And so we're getting some reflection from the global lighting, so we're not just getting lighting directly from a single source, which we do sort of in the olden days of lighting. We would have maybe one source total and get something like that, and so everything, the backside of the sphere would be black because there'd be no other way to light it. Unless we did sort of an ambient calculation that would kind of capture some of this. But what we're seeing is a very complicated set of mechanics in the lighting and the physics in the lighting. But we still see the properties of the Lambert and the cosine law here, where we're getting the full brightness value here, which is of course is kind of a gray, from our light and from all the sources. And then as we fall off here, even though we don't have a fully uniform lighting environment, we do see the darkening circle, right? It's pretty subtle. And of course you should take a look at this yourself so you can see it on your screen. You don't have to just hope that the video encoding was good enough to capture some of these subtleties. Okay, so we're going to continue working on our test material here as we play around with these properties. So seeing this, let's take a look at a texture map now. So we talked about the fact that the texture map is kind of our basis, so let's go ahead and actually bring one of those in. Let's see, it's called texture sample. So we'll bring in a texture sample parameter, and that's going to be our, we'll go ahead and call this albedo, and bring it over here. And again, we're getting the default UVs, and let's go ahead and change this default texture. There's a cobblestone texture, which is very nice here. Let's use this one. And this still lets us see, you know, the cosine property. We should see kind of a ring still, a darkening characteristic here, and it's sort of darker over here. But we also get a lot of the reflection of the light in the same way. And you know, we don't know exactly. Well, I guess we could look and see. So this sphere is it's a little bit hard to see, but we can see the individual triangle for one piece right here. And then if we come back to the lit view, we know that what we're doing is actually looking at that triangle, but within somewhere inside this texture map, right, and doing our whole process of linear interpolation. Okay, so here, so you know, we can, by setting the right parameters on the material, we can get something kind of approximates sort of a Lambertian model. And again, it's really just a very rough surface, so the microstructure of the surface is very rough. We assume that we're going to get kind of, we don't really care what direction our camera is. The color that's on it, say like right there, regardless of where I'm looking, is always the same, right? Modulo some maybe like the whole darkening that's happening here or something, because we're actually changing the exposure level. If I turn off the exposure, which I can do here, we do get sort of a darker scene, but we see that the light does actually stay pretty fixed, right? Okay, so let's dig deeper into the normal. So as we already discussed, we are getting a normal value that comes from our modeling, right? And so every one of these triangles has a blue normal associated with it, and that really represents the flat direction of, like the perpendicular to the surface that triangle makes at any point. And it's very easy to calculate that. You just kind of look and figure out which direction is outside. Sometimes you have to flip the normals to make sure they're pointing outside. But really it's very straightforward to calculate something like that. And so our modeling programs will do that, right? Based on what we've set up our triangles to do, we have a known normal for the triangle. And then for the vertices, the vertex normals, the vertices, we average the triangles around that vertex, and we get a normal for that particular vertex. So we essentially take, I've got 6 triangles surrounding this vertex. I take the sum of all of those directions and then divide by 6. And so it's sometimes, you know, it's usually fairly close to, because especially with a smooth teapot like this, all of the normals are fairly close together. If we had modeled something quite a bit rougher by creating sort of, well, you can see it right here, right? So there's kind of a rougher edge here, where now the vertex normals don't really align quite as well with nearby surface, the blue normals, because it is a rougher surface. So we're actually capturing more of the detail into each of the vertices. And then of course, as we already discussed, we will linear interpolate that normal, and it will give us the progression from, say, this vertex to this vertex as we move through this triangle, and we'll get a smoother sort of understanding of the curvature. So we can model sort of a macroscopic, we'll call it a macroscopic roughness when we're modeling by how rough we've modeled these how much we've pushed the vertices around to kind of create these creases and rough surfaces in terms of that shape. But depending on how many triangles we have to sort of add more triangles to get more roughness, and there's a limit, as we've said, of how far we want to go with that. And now we've talked about sort of the microscale roughness, so we can actually create what is essentially a sort of very uniform sort of atomic level roughness, where each of the particles is bouncing in almost an arbitrary way, so that we get a uniform scattering of the light away from the surface, or a reflection of light with this Lambertian model. So we're kind of capturing the micro level scale. But what if we wanted something in between, right? So we've got this surface here, and we wanted to have kind of a rough pattern that was not quite, you know, so micro scale that we can't see it, but actually something that's sort of at the human scale, or we'll call it a mesoscale roughness. And so so we use a normal map for that, right? So much as we've already seen that the texture map will let us get differences in color across a triangle as we move through that triangle, and it'll capture, essentially paint the texture directly onto our triangle for us. Now we can paint roughness. We can paint the normal onto there, paint the bump maps. And so You know, if you're used to seeing bump maps, which are usually black to white, so black would be the lowest part of the surface, and white would be kind of the highest part, or a very a grayscale in between. Then the normal map is really just the derivative of the bump map. So what's happening is that we've got normals, but they're encoded in color. Okay, so we've encoded the x-axis in green, or sorry, in red. We've encoded the y-axis in green, and we've encoded the z-axis in blue. So x is this way, y is this way, and then blue is kind of coming out at us, right? It's poking in our direction where we're looking in at it. We're looking in negative blue direction or something like that. So if I look at this, now there's one caveat to that, right? So I can only represent either all of red or no red, but I kind of need to represent negative x. And so what I have to do is, rather than saying I'm going to take, so if I've got a solid red, that means my direction is pointing this way, right? So the other two colors are 0, and I've got just 100% red, so that's what this edge looks like, right? It's a vector that's pointing this way. What's happening over here? Well, we have no red, right? Well, we actually have sort of a 50% red in the middle here. And so what's happening is we actually multiply, we can think of it as multiplying our color by 2, right? So that if the color goes from 0 to 1, then we kind of have 0 over here, and we multiply 0 by 2, and then we subtract 1 and we get negative 1. So negative 1 says if I've actually got 0 red, then I'm going to be pointing this direction. And if I've got 100% red, or all of the red, then I'm going to be pointing this direction. And in between, where I have 50% red, I actually have an x of equal to 0. So if we look at this and we say, if I'm at 0.5, and I multiply that by 2, I get 1. Right, so 0.5 times 2 is 1. Then I subtract 1, and I get 0. So if I take my red as 50% color and do this process to it, then I get an x equals 0. If I have 0 red, I actually get x equals negative 1. So I'm pointing in the correct direction. So we do that for all of these. So we have 100% green this way and 0% green this way. We kind of have this sort of weird space in between where we're actually at 50% red and green and 100% blue. Okay? And actually this right here is really a 50, let's see, we'll have 0, actually I think we'll have 0 both, no, we won't have negative. Yeah, so we'll have 50% green and blue over here, so it's really not a pure red either. So that's kind of why these all look sort of a purplish greeny color when you see them, because really every place where we kind of have a 0, or especially the flat surfaces that are pointing up at us, are going to be 50% red and green and 100% blue, because they're pointing at us that way. Okay, so that's why you get sort of this weird purpley color. It's a little bit 50% everything, except in the cases where the vectors are pointing away. And again, it's a normal, it's a direction. We want to make sure that it always has a length of 1, which means we can't have a 0 vector entirely, because that would be length 0. So one of these has to be greater than 0, and often one of them is 100%, and the other two are turned to zeros or 50% in the color value. So I've mentioned what's happening here a couple times, that we are taking the normal at each of the vertices of the triangle, and we're interpolating that normal using our bilinear interpolation that we saw. Same with the texture mapping, but now we're interpolating normals rather than positions in space, right, or the UV values. And so using these interpolated normals, we get a new normal value for every single pixel when we go to render it. So what happens then is that we build what's known as a tangent space at every pixel. So if we take the normal, which is our U-axis or W-axis here, and we use the same U and V as we had before, then essentially we have a full space that's kind of centered and positioned at each individual pixel, a full oriented space. And what we're doing is then we take the bump map at that space, and we look at the G value as going along this W-axis here, the R value is going along the U, and the B is going, or let's see, I said that wrong. B is going along the normal, R goes along the U, and G goes along the V-axis here. And so using those, we can position a normal in this space, a direction in this space, as the real normal, right? So in some sense, this normal that we get from our model is just a space organizer for us, and what we're really using, or space orienter, And what we're really using is the bump map to give us the individual normal within this overall space. So this helps us to handle the curvature of the whole model and yet still put in the very low level curvature of the individual bumps that we're dealing with. Okay, so before we move back into Unreal, let's take a look at really two lighting models. The first one is what's known as Blinfong, or Blinfong, and or just Fong, and it's another version of the BRDF function. So again, we have our light direction and our view direction and our normal, and those are what we're computing with. And what we do is we're going to care about a stronger reflection in this case with the Fong model. So rather than assuming that the surface is uniformly rough, we're actually going to look at it and say the surface now is uniformly smooth. And so the particles, the light particles, are all going to sort of perfectly reflect off that surface, or more or less perfectly reflect, right? So there's probably some amount of imperfection at the surface level, some microscopic imperfection. We're going to say it's a perfect surface. We'll sort of always assume we never have absolute perfection. However, it's mostly that way, right? And so given that, then, if we picture that happening, so if we picture all of our photons coming in and banging off this surface here and then flying this direction, if they're almost always going to perfectly reflect, then almost all of our energy is on this r vector here. So this is the reflection vector. So we take a look at whatever we could look at the angle here. So that's what's marked out with this particular diagram. The angle between the surface and the light vector is exactly the same as the surface and the reflection vector, right? So it sort of does exactly the same thing in the opposite direction. What we see is that all of our photons will more or less move in the direction of this r vector, and when they scatter, they'll only scatter kind of somewhat in slightly varying directions, but almost all of the energy is in this direction. And so what we do is we model it as a fall off, right? So we say most of the energy is going to be here, and then as you move away from this vector, it falls off very quickly, right? The light value falls off very quickly, and we lose it, and so it comes down, and by the time you're maybe where this view vector is, you're seeing very little of the light, right? So now what we care about really is the difference, or the difference in angle, not so much between the normal and the light, although we use that to figure out our reflection vector, but what we care about is the difference between the view vector and the reflection vector. So when we capture this, we say, we're going to essentially do the dot product between those, and then we're going to use a fall-off value to figure out how much or how perfectly smooth we think the surface really is. So if we look at it, it looks something like this, where for a very tightly smooth surface, and these are all essentially exponential fall-offs with different levels of power, for a very tight surface, we'll have, you are seeing pretty much all of the power here when you're looking directly at 0 degrees, right? So this is where the view vector perfectly aligns with the reflection vector. So you get nearly all the power, or most of the power from the source. And then as you move away from that angle, it falls off. So this one's a very steep angle, so this is a very, very smooth surface. And for less smooth surfaces, we'd have more of a gradual fall off, right? So we'd actually allow that the light's going to scatter. It's still mostly in the direction that of our reflection vector, but it now smears quite a bit more because of the assumption that the surface is not so perfectly smooth. So then if we take the sort of reflection Phong style model to an extreme, then what we have is essentially reflection mapping. Right? So this is maybe not necessarily a lighting model, except that it kind of is. What we're really doing is capturing a view of the scene around us. It's almost like reverse texture mapping, and we're projecting that onto the surface. However, what we can really imagine the scene is that's around us is our whole illumination. Right? And so we start talking about light models and the way lighting works, and especially global illumination. That's really how global illumination works, right? You don't just get the light sources that are hitting you. You actually get reflected light off of the other surfaces, because that light reflects off and then still hits you, and it's still light, right? It's still photons, and so there's no reason to ignore it in some sense. And so if we start allowing for large amounts of power from the reflection vector to come to us, right? So again, if we're saying that whatever photon hits us, it's going to kind of align in its reflected direction, and we do it very nearly perfectly, then maybe we can just say, well, if anything is hitting the surface here from the scene at all, we'll also show that light as well. Right? So it's kind of a first pass global illumination, what's known as a one bounce global illumination here, where essentially we see in this teapot everything that's around the teapot. And we'll actually see this in our Unreal sample as well. And it turns out that with subtle use of this, you can get something better than, this is often used now currently either as the global illumination component, so it captures that, or it's really what used to be known as the ambient light component. So we'd often, in older times with graphics, have not just a light source but an ambient component as well, so an ambient color, which kind of captures the overall ambient light in the scene. But of course the ambient light is not uniform by any means, and yet, for simplicity's sake, we would use a uniform lighting. Really, the lighting in a scene is very non-uniform. So it's all the different kinds of colors that you see in this reflection. Even, a little bit of blue here, some gold, some white and grays, and so on, or various shades of gray, really. And so by using even just some basic reflection, we actually get a better model of the lighting that way. And so our lighting model actually captures some of that at all times, except when we're sort of perfectly rough, because now it kind of dissipates most of that energy along different axes. So the way that reflection mapping works, in a sense, is we either have, say, a curved map where we've actually sort of captured like a wide angle lens, or something like this where we actually just capture a view in each of the directions, right? So we've captured a view along the purple one here, a view along the different purple, a red, a green, so on. We'll call that magenta, I guess. Literally speaking, we are imagining 6 cameras looking in each of these directions, and we capture the scene with those 6 cameras at any given moment, especially if we want dynamic reflection mapping. So it can be very expensive to do like a mirror in a game in this way, but it is possible. And so we capture those views, again, from the perspective of the camera in the 6 directions. And then what we do is when the light comes in, or from the view direction, we sort of work backwards, right? So we want to find out, because we have essentially infinite light sources in this case. So if we come back to our Phong model here, every pixel in that image is a light source. And so what we really do now is just take the view direction and then figure out what reflection vector, right? So we sort of reverse the reflection vector. We find out, well, what light source am I actually looking at? Where is the light source coming from? So we kind of take the reflection vector of the view itself and then sort of back propagate and say, well, okay, that was where the light came from. So that's actually the reflected light that we're seeing. So we take the view direction, we reflect that, and then we project it out into the scene and figure out which of these surfaces we're hitting, where we're hitting it, and what the texel value, what the pixel in the image value looks like at that position in space. So that's how reflection mapping works, and we're using that. And I said multiple times that we're kind of using this as we captured the camera view from here. The way we tend to use it in games, if we're not going to do global illumination, or we're not going to do dynamic reflection mapping, is that we'll capture essentially a view, a sort of distance view, if you will, like a skybox. So rather than capturing near elements, we'll just capture things that we figure are relatively close and sort of make sense in the scene, but the scene itself is much smaller than what's being captured in here, so that all of the objects can use this. And we've already seen this in the Unreal preview viewer, where we're looking at a scene sitting on a small table, and the office park is sort of around us, and so we're seeing the office park. So let's take a look at that and see both the specular response, the reflection mapping, and then the bump maps as well, and how that all works. And so now we're back in Unreal. Let's take a look at how this works. So before I get too far, I'm going to put a simple color back in just so we can see the difference. Actually, I'll set up a gray here, something in the mid-range. And I'm going to continue to use my 1 and 0 parameter here. So let's first take a look at what the specular looks like. So I'll bring in 1 on specular and then 0 on roughness. So now what we're saying is we have a specular surface. We're going to do the kinds of, this sort of the Phong model of lighting. And of course, to do that, we need the perfectly smooth surface, right? So that we actually get a reflection out of it. And the specular here really amounts to, think of this a little bit as the fall off, right? So if I lower this value, if I actually set it to something like 0.5, then it starts to blur some of this fall off a little bit, and so we get not quite as strong and so on. Maybe around 0.1 we start to get a real bleed value, right? So what we're really seeing is, so we don't see the light so much here, or the light source as a strong component, sort of somewhere out there, but it's not a terribly strong one to create a real reflection point. We do see the reflection there, but what we're really seeing is in some sense the reflection of the environment map in this case. And so we're seeing the combination both of a single light source, which is also causing the shadow here, in combination with the global source, which is the view around us, right, which is all of the office park here that we're sitting in. And so that contributes essentially as a full light source, both from, in terms of our specular result here. And so that's why we see the reflection. Of course, it sort of jumps, Unreal jumps us into essentially more advanced graphics. So we're now, if we want to see a full reflection vector, then we'd use the metallic component and set that to 1. And now what we have essentially is like a silvered surface, right? So this is like what you'd use as a mirror. And then it's a perfectly smooth, perfectly reflective kind of surface, right? That then is actually capturing the full office park view. So yeah, so we're seeing now the actual full reflection mapping. And of note, I guess, is the fact that we've been talking about the eye as a single eye position, but if you recall, the eye is really sitting behind the screen to some distance, and what we're really doing is casting a point, a ray from, say, where my eye position is through the screen into that pixel, and that gives us a slight direction, right? So the only point where you're sort of directly into your eye is the center view of your screen. So, but each of these is a vector which is slightly offset, has a slight angle to it along the horizontal or along the vertical. And so that's really the vector that we use here. So that's why you get slightly different directions, right, as you might expect. So then that's our actual eye vector, and that bounces off, and then using that vector, we find where we are in this map here. And I believe this map, looking at, is probably a cube map. So there's actually, somebody came here and took a camera view from each of the 6 angles, and they're put together seamlessly so that they look like a full surround. But now let's plug in our texture map again. So let's go back to, let's see, we've got the 1 on the specular, let's put the 0 back on the metallic. This is a specular component for non-metallic surfaces, so you shouldn't have both, I think, together, but that's okay. So let's go back to, oh no, I think I'll leave it here. So let's leave, we'll see the small amount of reflection. This really doesn't look quite right for the surface. It looks like we've got sort of a marble, right, with a shellac coating or some kind of coating on the surface, and that looks great because now we can play around with what happens when we bump that. So let's look at the bump mapping. Come all the way back to how texture mapping works. So we're going to bring in a texture sample again. Okay, so we brought in our texture sample with the normal map now, and so what you see is so the reflection has changed quite a bit, right? It now doesn't necessarily feel like we've got sort of this shellacked surface on our ball, but really that we've got sort of a shiny surface on each of the rocks. And so what's happening is, again, if we think of our eye vector as hitting the surface here, then the way that we decide the reflection is based on the no longer the normal of the surface or just the broad normal of the sphere, but it's actually the more precise normal of each of these rocks, right? So the rocks, if we look here, we can see kind of the red and the green that we expect where it moves, along the edges. And so we know that this rock, the normal casts out this direction away from the rock, right? And in the center, maybe it's sort of looking more or less at us or in the direction of the sphere itself. But what that gives us is then the lighting changes no longer sort of uniformly across the sphere or in a way that's sort of spherical, but it follows a roughness pattern. And that's because, again, we have sort of, if we go back and look at all the way to the beginning here of the per pixel normal, where we're moving across the surface and getting different normals, and really getting different normals not just from the smooth interpolation across the sphere, but actually capturing all of these different changes in the normal value. Then that gives us individual normals and gives us a much more precise, a more complete level of roughness. Now the next technique we'll talk about here ends up being kind of a throwback to 2D when we're doing parallax, and we'll see that in a minute. But the idea is that with a standard texture mapping, as we've seen, you sort of just get the color back. When you do normal mapping, you get lighting variation along the surface. With parallax mapping, you bring the bumps back in, and so you actually get extra information about where things are in space. So what you're seeing here is that because this lion's head is poked out to some degree, and because we're seeing it sort of an off angle, the nose is shifted to the right, and these sconces, I don't know how to pronounce that word, also shift based on their heights, which are a little weird here, but they're still shifting. Really, the lion's head is probably the most dramatic point here, that it looks more 3D. And we're using really the same parallax trick that we talked about being used in 2D, but we're doing it with the texture map, so it's on the surface here. So we're kind of you can almost think of this as slicing the texture into layers based on their heights, and then shifting those layers, much like we do with the parallax layers, based on where the eye is and the angle that it makes with the surface, and we sort of shift those layers that way. So we're going to come back. So recall that the bump map is really the derivative of the normal map is the derivative of the bump map, meaning that we sort of see the directionality in 2D of the bumps, but we can kind of go back and forth, right? So we can see that if we've got this bump shape here, where we've got kind of that direction and so on, we know that the grayscale represents height, right? So where it's darker, it's lower, where it's brighter, it's higher, and then we can get the directionality out of the normal map. And so we use, to some degree, both of those to help us figure out not just how much to shift, which is kind of how high it is or how close to the eye it is. So if it's whiter, it's closer to the eye. If it's blacker, then it's further away from the eye. And so we use that to tell us how much to shift. We sort of treat that as our very cutting this up very finely into maybe say 256 different layers, and we shift those layers based on, again, how close or far away from the eye in the direction of the normal. So I've kind of talked through this, but let's take a look and remind ourselves what parallax looks like. So if we're imagining that our eye is moving from left to right, then things that are closer to us kind of move with us, right? So they move quickly, in this case in the opposite direction of what we're looking, but things that are further back move slower, okay? So what that means is that as we make angles, as our eye makes an angle with the surface that we're trying to texture map, then things that are closer are going to move more dramatically. They're going to be offset more dramatically than things that are further away from us. And they're going to be offset sort of in the opposite direction of our eye, kind of almost like a reflection in some sense, in terms of where the offset occurs. It looks as though it's pushing away from us if it's higher, right? And so we can see that again with the lion's nose. We're off to the side here, and so we're pushing the nose in that direction. And actually, it's the reflection vector, so it does include the normal direction and so on. So it is very much like a reflection map but we're actually shifting the pixels. We're kind of shifting our interpolation of the UV indices and which texels we actually grab out of our texture map. Okay, so whereas normally we would just interpolate and find our U and V values, this really shifts those UV values, so we're grabbing different ones. And that's kind of how this technique works. So let's take a look at it in Unreal so that we can see it in practice. To set this up, I'm going to grab yet another texture. Actually, I probably should have named that normal, so let's do that now. And bring in another texture sample. So the last one that we have available from our cobblestone set. Now this may actually be, I don't know if this is intended to be an ambient occlusion map or a height map. It kind of works for both, so we're going to use it for both in the end. But we're going to use it for heights here. So again, what we're looking for is where it's brighter color, or where it's white, more white than black along the grayscale, it's closer. And so the brighter the color, the higher it is, the closer to your eye, and therefore the more it shifts. And so the darker it is, the less it will shift. And so I've set it over here because what we're really going to do is take it and offset the UVs of our albedo and our normal. And so because and also we really only care about the grayscale value, so we don't necessarily care about individual colors. And in fact, we can't pull a full RGB element, so we just pick one of these as the value that we're going to use for height, because they all should be identical values, maybe not alpha in this case. So let's pull that over, and what I'm going to do is put in a multiplier with a scalar parameter. Mostly so that I can switch it between 0 and 1 easily, so we can see height and no height, and we can see the offsets that way. I'm going to pull in the bump offset node. Actually, let's go ahead and just pull everything this direction to make some room. And I'll plug that in. And then we'll plug in the UVs here. Okay, so you may not have noticed much of a change. In fact, because there's a 0 scale here, there's no change, but I'm also going to change where I'm looking. So I'm going to grab it from the side here because it's a little more dramatic, and we can pull something that looks a little bit like our sample with the lion, but using the textures that we have available. And what I'm going to do is shift the scale from 0 to 1. And what we're looking for is that the things that have white values in, or closer to white values in the texture here, should have been shifted away from our eye, right? And if I set it back to 0 and back to 1, and I encourage you to kind of pause the video and rewind and look at these things so you can see it's actually fairly subtle, but it's enough that you start to get a sense that there is a 3D texture here, right? So without actually changing anything, and of course if we look at this side, we know that it's perfectly flat, but looking at it from an angle, and often, you know, if we were to imagine this being on the street or on the ground, then we would actually see this offset a little better, because this is kind of the direction that our eye would see. Really, it's more like if we were looking from here, but because the lighting is a little bit flat, more flat looking over here. So and you know, that's a call out to when you're designing it. You might be careful about designing your lights so that you can play these kinds of tricks. If I haven't already said it in another lecture, much of what we do in games to make them work is a lot of smoke and mirrors, and you know, like movie magic, right? If you've been to Hollywood, you also know that all the houses actually don't have interiors, and often you're just seeing the front side of the house because that's all you need to convince somebody that they're seeing a street. Very similar kinds of things happen in games. We sort of make sure that you're not looking at the thing we don't want you to look at, right? And so you should keep that in mind and carefully select things so that you can get away with a lot of tricks. So let's also see, we could actually scale the height much higher to make it a little more dramatic, and we start to see where you know, this technique will break down. So if I scale it up to 2, then there's a little bit too much parallax, and we start to see we're shifting a little too hard with some of these things, and it actually skews the image. So there is a breakdown. We can't just sort of arbitrarily shift these things along the view axis here to make it feel like it's 3D, because it's not. So there's a limit. But with a height scale like this, you can kind of push it a little bit, and maybe, if you feel like that wasn't significant enough, if the one value wasn't significant enough, we can use 1.4 and get maybe a more dramatic feel to it. I still don't think, it's a little better, but it's still pretty flat because of the lighting again up here. So the next technique we will show here, we'll talk about, is what's known as ambient occlusion. So the idea behind ambient occlusion is that, so we're seeing it here on a grayscale image, where what we assume is that we have a hemispherical or spherical light that's all uniform, all sort of perfectly, a perfect white light that casts its light into the scene, but it's not in the scene. It's sort of completely distant, but a uniform sphere. And so what we'd expect is that, if, say, we were lighting a sphere itself in the center, it would be uniformly the color, right? So that would be kind of what we'd expect from, say, standard texture mapping. Or if it were a white sphere, it would just be white, right, or gray. Here, what we see is that if we imagine the light bouncing in, right, and we do a full global illumination, then the surfaces that are exposed to the light, to the sphere, are fully lit, right? And to some degree, they're not necessarily white. They're sort of a grayish color, which is fine. But we get the lighting on the surface that are exposed, and the ones that are not exposed have to get indirect light, right? So, for instance, underneath here, where we see the shadowing happening, we're getting only bounced light coming in. And so the intensity is less. So the idea with ambient occlusion is, one, that we don't actually apply color. We're only worried about intensity in this case, right? So we're kind of looking at, what is the average intensity pulling away, and so maybe, these surfaces aren't perfectly white, so they don't necessarily reflect all of the lighting that they get, but they reflect however much intensity they're going to reflect. These surfaces do, all of the people here do, and then everything that is not getting direct light gets less intensity. In the very deep corners, what you can imagine is that, again, coming back to sort of the probability of photons and the idea that billions of photons are going to land, and we're going to do the law of large numbers. Where it's dark, the probability is very low for photons to get in there. So regardless of how they might bounce in, from which direction they might bounce in, it's very hard for a photon to get sort of inside this little region right here next to this. It's very hard for the photons to get underneath the house, and so very few photons get under there, if at all, especially very far into the house. And so what we end up with is essentially sort of a probability of how the light hits, assuming sort of a uniform source and all the light from every direction can hit. We get kind of the overall probability of how the light hits, and so we can capture and bake this into our model. And now we know, in some sense, when we use, say, even our office park scene, we can modulate the light coming from that scene to know that we're gonna reduce the intensity in the various regions where the ambient occlusion is strongest, where it's actually being occluded, and that's why it's called that, right? So it's occluding the ambient light, sort of taking into account all of the ambient light, and then figuring out where the dark shadows are. It's kind of the creases, and so we really do this per model. So we can do it per scene, and we'll talk about that when we get back to global illumination and post-processing. We can capture a full scene's lighting, but really what we're doing is capturing it for an individual. And so this individual has a lot of wrinkles on its face, this particular model. And so to capture those wrinkles correctly, what we really want is to capture the ambient occlusion for this model in exactly the same way. We use a hemispherical light, although we do have a non-direct light source here that's also added to the model. We use a hemispherical light to say, where is it hard for the photons to get in? And it's all these wrinkles, right, that are in the face and in like where the eye cavity is, and next to the nose here, because those are sort of narrow crevices where it's harder for light the photons to sort of get in there, lower probability of getting in there. And so we darken those regions, and we get a stronger sense of the overall lighting, and we can use this then in a variety of lighting environments and capture what's happening with this person's head, right? This model here. Now it's worth noting that this is baked, and so it might be the case that if we were to start animating the face, that we would break down where these wrinkles are. We wouldn't quite necessarily move the wrinkles in the right way, or there might be new wrinkles forming, or ones that are stretching out that should no longer have ambient occlusion. And so because we've baked it, we might have too much ambient occlusion, but it's a fairly good effect, right? And usually we can keep it to small degrees of animation, but it also happens if you imagine capturing sort of the armpits and knee pits and crotch and so on of those are also darker regions if we capture the full model. And as you're walking and swinging your arms, those regions become lighter or darker depending on how you're stretching that out as you move through space. So it doesn't necessarily work with animation. However, it's a fairly resilient effect, especially for the small scale effects like the wrinkles and so on. So let's take a look again in Unreal at how that looks. This effect is going to show up fairly light. We're not actually going to be able to see it very well, but it's pretty much a straight line. So I'm going to pull it from this our supposed height map over here and use the same value as though it's a ambient occlusion map. And you probably noticed no real change, right? So it is here and it's available, but it's a very subtle, especially in this lighting environment, it's very subtle in its overall impact to the texture. But again, it's available and you can potentially use it. So the final material technique we'll talk about here is actually not really a material at all. It's a light source in the material. So this is where we can actually embed lights into into our material when we're trying to render them. It's often used for global illumination. It actually doesn't work that way in Unreal, but it can be used for other post-processing effects and to get the essential character of a light on a texture, and it works fairly well in say darker spaces or whatever. So let's take a look at that. It's also a case where if you have a patch where you simply want to ignore lighting for some reason and just have it be some color, so here we've got this reddish color sort of showing through, then you can add the intensity that way, or just get the extra intensity where you want a strip of material. So let's take a look. I'm going to artificially modify our overused grayscale texture here and add in the vector parameter. And let's do a bluish kind of light here. We'll put on this. Okay, and then what I'm going to do is scale my grayscale by this color so that I can get some kind of uniform color added to my emissive color here. Then when I bring this in, we see that it's just really kind of broadly adding this bluish color to everything. So it's because we're multiplying this by the bluish color, we really get just an additive color to the whole thing. And we can think of it as if I turn off the exposure, and let's see, maybe I'll darken the exposure. What we see is that it's really sort of independent of the lighting, right? We get this extra color to our texture. And so this is just additive to that location. Now, what you'd probably do more than likely is isolate regions of your texture. So I might say, if there's a particular rock I wanted to highlight as being bright, or if I'm in the interior of a spaceship and I have sort of lighting on the walls that guide along or something like that, something closer to what we saw in our example here. That's really where you'd use that kind of texture setup. But this is where you have access to it again. And so that's the full material suite. That's pretty much what we'll talk about here. Let's look at an example of bringing in the full set. So you might have been wondering how to get some of this stuff put together, and of course modeling is outside the scope of this class. We're not going to look at how we actually model or how we might create ambient occlusion, but we can look at where we can get a hold of some textures that have ambient occlusion. So there's a lot of things online, folks online who have put things together to sort of make this kind of thing possible. And here's an example. So what I've the CG bookcase are all free textures, they're full PBR, and from the set are a lot of the pipelines that we want over here, right? So all the pipes that we just talked about, the base color, the metallic, the specular, roughness, and so on, are all set by textures, right? So for instance, the metallic here is really just pure white because this is a bronze material, and so it's all metal. But you can see that the roughness is changed, so it's actually fairly rough in some places and fairly smooth in others, and so you get differences in that material. The normal map in this case is not necessarily interesting. In fact, this is a normal map where it's really just directly up, right? And so that's why it's all blue. We're seeing half red, half green, and so on. But if we look through all of these textures, then or look through this whole set, we'll find a wide variety of textures that we could use and apply this method to. And especially one of these two is the bark that I actually used for the example here. So let's see what that looks like and how we import that. So I'm going to come over to the project map here, and I've created this folder called bark, and I'm going to drag my content into there. So I've downloaded them onto my disk here, and I'm just going to drag all of these textures over, and it creates a new texture set that I now have available. So along with that, I'm going to go ahead and just create a material to work with. It's going to be my bark material. So then I'll come in and bring in all of my parts here. And you notice I'm skipping time here. I don't want to take up a lot of time, but hopefully you're able to look at this and understand the steps that I'm going through at this point now that we've gone through them. Certainly it's worth practicing this kind of process. Okay, so I've put this all together, and it looks fine. We see that all the parts are in play. However, you'll notice that my coordinates are slightly off, so let's take a look at how we might resolve something like that. So I'm going to bring in the text coordinate. This is actually a 2D value then that represents my UVs, and I can bring this in and apply it to my heights here, and I can apply it to the coordinate that I'm actually going to offset over here. So if I were to do that, by default this is what's being applied. So we see that nothing changed because it didn't actually change the coordinate. What I'm going to do is create a new scale for U and V. I'm going to use a node called append vector, which what this is going to do is take these two scalar values and turn them into a single 2-vector value. So I know that my text coordinate over here is a 2-vector value of U and V, and what I want to do is multiply by my scale here and use this as my input. Now when I do this, it's going to break it because I've actually set the scale to 0. Let's go ahead and set the scale to 1 and 1. And we get back what we had, but I want the scale on the U to be 4 because this bark was roughly 4 to 1. Right? And so doing that, now I get the bark back, and in fact I can do a cylinder here and I get something that looks more like the bark. So given all this, we get a fairly nice representation of the bark. We can use all of the channels that we're used to. Hopefully you see maybe a way to deal with some non-standard textures as a process here. But also put everything together and see a final output minus maybe emissive color, because it doesn't make sense to put lights on the bark. Unless of course you had maybe some reason to for a gameplay reason. And yeah, I might also want to come in here and ensure, in fact I'll do that, I'll say I want to make sure that I have no no metal and no specular as well, just to ensure that those are set to the right value. And finally, we see the expectation here. Now again, you know, unfortunately the AO effect is fairly subtle, so it's hard to see the full effect, but in the full instance. But we do see, you know, all of these taking place, including the bumps and the normals and so on. So I encourage you to go take a look at the CG bookcase here and browse through and try to put some of these textures together into new materials that you can then use and place in the world. And so the final step, actually, before we take off entirely, would be to apply one of these materials and take a look at it. So we can put down some bark. This one maybe doesn't look quite like we'd want, although I could change my UV scale to make it a little bit smaller. So I'll show you a version of that. So we've got our UV scalars already. So if I change these to, say, 32 and 8, if I come back in here, now it seems a little bit, you know, more to the size of the scale. And of course, this is because our UVs on this block are just from 0 to 1, and so they're really just scaling that UV. So even if I bring in my test material over here, same kind of process. But you can take advantage of this kind of texture scaling in order to not have such a huge texture, you know, when you want to actually have this kind of effect happen, right? So that's the way we put this all together, so we can start modifying the materials in our level. And one last thing I'll show you, just as a way of seeing the other kinds of BRDF style functions. There's one that's known. There's a final technique or a function known as subsurface scattering. And so this is an entirely different process to what we've looked at so far. It's still capturing the input radiance and the output radiance, but in this case we actually keep track of not just a single position, but we actually have sort of the possibility of scattering through a material and capturing light from layers inside the material. It's almost capturing the volume, and so we get things like the blood that goes through the human hand, or just the thickness of the material is almost captured by how much the light is scattered or not scattered by the full material. So a porous or softer material allows the light to come in, bounce around for a while, and then leave. And so skin is really that way. So the only way to get skin correct is to include subsurface scattering. So I will briefly show that this is the case, but it will let you kind of play around with that on your own time. There are different shading models here. So we have a default lit, which is the case for what we've been using thus far. But we actually have subsurface as an option, which includes the subsurface color. Then you can blur in the kinds of things that we just saw, where we actually capture some model of the subsurface. We actually have pre-integrated skin, and then some other shading model types for different kinds of surfaces that are maybe a little more complex than simply metallic or specular, the sort of the plastic set, by changing the broader lighting model. So it's much deeper and richer than even what we've sort of explored thus far, but certainly take your time to play around with these models, try to integrate them into the scene, and you know, make your game look that much better.